Hey, pre-calc students, we're going to take some notes by hand today on Unit 7, Day 4. So we're in our logs unit. We're going to be talking today about two really important concepts, one of them being something called the change of base formula, which we'll get into in just a few moments. And then beyond that, we're going to talk about how do we find the inverse algebraically of both exponential and logarithmic functions. So before we get into that, here's a quick review of something I hope know how to do from Unit 6. If I gave you an exponential equation, such as 4 to the x equals 8 to the x minus 1, if we wanted to solve this, we would think about making a common base. And with bases of 4 and 8, hopefully you would think about dropping those maybe down to base 2. And once I do that, we can express the left side as 2 to the second power. So that would become 2 to the 2x. 8 is 2 to the third power, so that 3 is going to get distributed to the x minus 1 that's up there. And if we continue to solve, we get 2x equals 3x minus 3 after distributing. And if you switch the order around and combine like terms, you would get x equals 3. So that's pretty easy for us to do, I would say, at this point, making a common base on both sides and then setting the two exponents equal. But the question becomes, well, what if you can't establish a common base? So what if it's not possible to drop them both down to base 2 or base 3, or we've done base 5 and things like that. So for example, if I gave you 7 to the x equals 12, there's no way that I'm writing both sides as a common base right now. So if we think about what we did in the last unit, we would have just solved this graphically. We would have done y1, y2, and we would have had to approximate our answer in the end, round to the nearest tenth, hundredth, something like that. Well, we can express our answer in an exact form and solve for x using one of two methods. So there are two methods that we'll see in order to solve this. So in method 1, what I'm going to do is I'm going to wind up taking the log of both sides. So I'm going to take log of 7 to the x and then log of 12. Log is a function, right? So it's an operation. So it's kind of like taking the square root of both sides, right? We're going to take the log of both sides. Why does the operation taking the log of both sides really help me? Well, what I'm hoping to remember is one of those properties of logs says that if you have log of something to a power, that power can come to the front. So we get x times the log of 7 equals log of 12. Log of 7 and log 12 are really just numerical values. So you can divide log 7 to the other side and get x equals log 12 over log 7. Now I can go to my calculator, get the decimal approximation, just like I could have gotten a decimal approximation up here by doing y1, y2. Okay, but this is what we call an exact answer. Okay. So when I say round to the tenths or the hundredths, that I think is pretty clear. But if I say to express it in an exact form, you would leave it in log form and not actually type anything into your calculator at that point. So what's the other technique to solve then? Well, the other technique is if I go back to 7 to the x equals 12, is to not just take log of both sides, because when I took log of both sides over here a moment ago, I was using log base 10. Right? I was taking a common log of both sides. And the only reason I like log base 10 is that, like I said, I guess I should tell you guys the decimal. Sure, why not? All right, so we can get an idea here, okay? Because I have log base 10 on my calculator. I have that button that says log right here. So if the solution is log 12 divided by log 7, I know that the answer should be somewhere between 1 and 2. And the answer here is 1.28 to the hundredths place. So because 7 to the first is 7, 7 squared is 49, which is way too much already. I knew my answer should be somewhere between 1 and 2. All right, so how would I do this otherwise if I wanted a similar technique? So what you can do is you can choose to take the log base of both sides with whatever base that exponential is. So make the base of your log match the base of that exponential function. So I could take log base 7 of both sides. And from there, what we'll see happen is when I'm taking log base 7 of 7 to a power, log base 7 and the base of the exponential 7 undo one another. These are inverses. So you just get x on this side. Okay, so x is equal to log base 7 of 12. And what I want you to do is I want you to look at these two answers. And notice that although their appearance looks different, these two answers are in fact equal to each other. Okay, so they look pretty different, but log 12 over log 7 is the same thing as saying log base 7 of 12. And next time we're in class, maybe I'll even show you a way to prove that on the calculator. But what this kind of leads us into is what's called the change of base formula. So if you had something that you wanted to change the base, if you don't like log base 7, you want to change to log base 10, we're going to use this equivalency right here to kind of guide our work and say the change of base formula is the following. Change of base formula. If you have log base A of x, if you wanted to change to log of another base, look at this, log base 7 of 12, it would be log of the value x divided by log of the base A, right? It became log of 12 over log of the base value 7. So these are going to be equivalent expressions, okay? Or it doesn't have to be log base 10. It would actually have been the same thing if I had done the natural log of, in general, x over the natural log of A. And I can prove that to you by saying, hey, if we still have log 12 over log 7 typed in, what if I had done natural log, ln of 12 divided by the ln of 7? That's also going to be the same decimal, 1.28. So how cool is that? You can change it to whatever base you want. So in fact, or you can change it to log base b of x over log base b of a. You can change it to whatever base you want. Okay. So if I ask you to evaluate something like find the log base 5 of 120. Log base 5 of 120, if you wanted to, you could express as log of 120 over log of the base 5. Use common logs, log base 10. Or if you love natural log, ln of 120 over ln 5. And those should give you the same approximations. So let's double check that. Log of 120 divided by log 5 is about 2.97. And if I do ln of 120 divided by the ln of 5, that is the same thing, 2.97. I would say it's probably especially helpful when you get into instances like the log base 4 of 32. So if I have log base 4 of 32, there's really two approaches that we have to solve something like this. The approach that we've seen so far is to say, well, that equals some number x. And if I convert that to exponential form, 4 to the x equals 32. And I can solve that equation, and I'll come back to the side in a second. The other approach, though, is saying, all right, if I have log base 4 of 32, if I use the change of base rule, what base would make sense to choose for 32 and 4 such that it's easy for me to evaluate these logs? And it turns out that 4 and 32 are related with base 2. If I was solving this using common bases, which I'm about to do over here in a moment. You can change this to log base 2 of 32 over log base 2 of the base 4. And log base 2 of 32 is 5 because 2 to the 5th power is 32. Log base 2 of 4 is 2 because 2 squared is 4. So I can quickly come up with that answer of 5 halves. Over here, you would do something really similar where you would say, all right, well, this is 2 squared. You have to have the same logic, don't you, right? 2 to what power gives you 4? 2 to what power gives you 32? And if you set 2x equal to 5, you do get x equals 5 halves as well. So kind of a quick way to evaluate there. In the end, could I have also checked by doing something like log of 32 divided by log 4 to see that we get exactly 2.5? And the answer is yes. Okay. So we're going to see this as a technique for solving using this change of base idea. Okay, so kind of as a final example to wrap that up, if I said to solve the equation, 3 to the x equals, let's do 140. It's a couple different approaches you can use there. If you like the approach before where I did the log base 3 of both sides, students tend to like this, where they have the base of the log match the base of the exponential, because these are inverse operations. Log base 3 of 3 to some power is just that power x. So x equals log base 3 of 140. So this is the exact answer. If I said also to round that to the hundredths place, how would I do that? Well, I'd need to maybe quickly use the change of base rule, where I take log of 140 and divide by log of the base 3 to figure out that decimal approximation. So log 140 divided by log of 3 is 4.50 to the hundredths place, if I go out that far. Okay, so rounded, we would get 4.50 approximately. So we should be able to use our new rule with change of base formula, and solving these exponential equations, we should be able to do that hopefully pretty easily now that we know that rule. All right, last thing we're going to do today is talk about finding inverses algebraically. We haven't maybe talked about inverses in a while, but it's a topic from last year in Algebra 2. It's a topic from our course this year. If we think all the way back to our functions unit, what we want to do is to find an inverse, switch x and y, and then solve y again. So if we get f of x equals 3 to the x plus 1 minus 4. Okay, if I want to find the inverse of that function, the first thing that I like to do is I like to get x's and y's in there. So I'm going to write it as y equals 3 to the x plus 1 minus 4. And then we know that based on the process I just described, we're going to switch x and y. X equals 3 to the y plus 1 minus 4. And to solve for y, you have to isolate the base of the exponential term. Okay, so whatever's next to that base 3, in this case, it's only subtracted from 4. You have to get that alone first. So I'm going to take x and add 4 to the other side. This just becomes 3 to the y plus 1 power. So that wasn't too many steps to isolate the base of 3, but if there's more than one thing happening to base 3, we'll have to take care of all of that. So now that I have the base isolated, what do I do to get rid of and undo raising 3 to a power so that I can solve for y? You're going to take the log of both sides. If you have something that's exponential to start, the inverse will turn to logarithmic form. All right, so we're going to take the log of both sides. Now, we can choose whatever base of a log we want as long as we're consistent on both sides. What I'm going to choose to do is I'm going to take the log base 3 of both sides. And I think that will make sense based on what I did actually just right up above and solving up there. Okay, so when I take log base 3 of both sides, it's log base 3 of the quantity x plus 4, log base 3 of 3 to the y plus 1. What would happen on the right side is you would just get y plus 1 left over. Okay, the log base 3 and 3 to this power, they undo each other to just be left with y plus 1. Here we get log base 3 of x plus 4. So in the final step, if I subtract that 1 to the other side, y would equal the log base 3 of x plus 4 minus 1. And the last thing you can do if you want to be fancy is write it in inverse notation. F to the negative 1 of x would equal log base 3 of x plus 4 with a minus 1. Okay. Let's just try a few others to make sure that we're on the right track here. So if we have f of x equals negative e to the x plus 8, find the inverse there. So I would change this quickly over to y equals negative e to the x plus 8. And then switch x and y. X equals negative e to the y plus 8. If I follow the steps from earlier, we're going to isolate that base. The base in this case is base e, and then eventually take some sort of log of both sides. So if I subtract 8 to the other side, x minus 8 would equal negative e to the y. You have to, in this example, divide out the -1 that's in front of the base e. It looks like base e is all alone, but it's being multiplied by -1 right now. Got to divide that over to the other side before you can introduce a log. Okay, students do commonly forget that step, so you'll see it come up here and there. But divide out the -1. What happens is it becomes -x plus 8. And by the way, I have nothing against you writing -x plus 8, but sometimes I get fancy and I write it as the positive 8 out front, 8 minus x. So it doesn't matter, but in case I get fancy on you in the future, I just wanted to make sure you see what that form looks like. That now equals e to the y. Good. Now we're up to the step that base is isolated. And if I think about taking the log of both sides, I'm not going to just use log base 10 or log base 3. Let's be smart about our choice and think about what log base is the inverse of the function e to a power. And because e is the natural exponent, of course, we have the natural log ln that you can use on both sides. So you're going to take the ln of both sides as the most efficient way of getting y alone. Ln of e to the y is just y. So y equals the ln of 8 minus x. And therefore, your inverse, if you wanted to rewrite this, would be the natural log of 8 minus x. Okay. I'm going to do one more with you. If you're feeling like at this point, you know what, I kind of got the process. I'm going to try this one on my own. Go for it. Okay, but the last one we'll do is, let's go with g of x. We've been neglecting g here. -3 to the x plus 5 minus 4. Okay, I'm going to do this one a little bit faster. Make it y, right? So we're going to switch x and y. X equals -3 to the y plus 5 minus 4. We're going to add the 4 to the other side. And the only reason I wanted to do this one is because, again, we have that negative in front of the base. You cannot, at this point, take the log of both sides until you get rid of that -1. So when I divide both sides by -1, this turns into -x minus 4 equals 3 to the y plus 5. Okay. Now you can take the log of both sides, and I'm going to choose log base 3 because I think that makes sense if the base of the log over here or the base of the exponential is base 3. Okay, so take log base 3 of both sides. This becomes log base 3 of -x minus 4. This would become just y plus 5. And in the final step, y would equal log base 3 of -x minus 4. Subtract the 5 over. So using inverse notation, I'm shocked I'm remembering that we're using g here. I usually always write f, but we like g of x sometimes too. Okay, log base 3 of x minus 4 with a minus 5 attached to the ends. Okay, so that's it for today's lesson on inverses and some change of base rule. Next time I see you, we'll do a lot more practice with these two concepts. Let me know if you have any questions. Have a great day.